Hello and welcome to Chapter 22, Organic Chemistry. In the background here, you might hear my baby cry. She's taking a nap, or you might hear my dogs chewing on their bones. So ignore that. Alright, so here's what we're going to talk about. And you'll actually probably spend a good year of college chemistry on organic chemistry. It can get really complex, but we're just going to learn how to name a few things and to understand the basics. Some interesting history behind organic chemistry. It was thought, way back when, that living things produced compounds that we couldn't synthesize in a lab, and that we would only be able to study if they came from humans. But then one day, this very interesting fellow, Frederick Wohler, ended up creating urea synthetically. What's urea? Well, it's in your pee. So that was a huge discovery that sounds kind of crazy, but he figured out that he could synthesize something that was produced by human and animal bodies. And because of that, it's led to discoveries for all kinds of compounds that help us medically, just in our lives, like any type of fake sugar is essentially an organic compound, and it's led us to study a lot of things. But what organic chemistry is really about is carbon and hydrogen bonding, and sometimes there's some silicon in there too. So we're going to talk about hydrocarbons. Well, guess what they're a combination of? Hydrogen and carbon. And if we call it saturated, it just means that there are no double bonds. It's the maximum amount of hydrogen and carbons that can be bonded to each other. So if there's no multiple bonds, they must all be single bonds, so these must all be sigma bonds. And they all have this general formula where however many carbons we have to multiply that by 2 and add 2 in order to know the number of hydrogens, which makes sense because how many hydrogens can bond to one carbon? 4. So it really makes sense if you look at the formula for that. Okay, so alkanes are carbon-hydrogen single bonds, and they're always in a straight chain, or they don't have any branches off of them if we call them unbranched. And we can name these really easily by using a prefix for the number of carbons and ending them in ane. You've heard of propane. Well, that's something that might be in a gas stove or heater, and it's actually a straight chain hydrocarbon. And how many carbons must that propane have in it? Well, look at our little chart here, 3. So we have methane, which is farts, ethane, propane, butane. Have you heard of a butane lighter? Well, it has 4 carbons in it. Pentane, hexane, heptane, octane, nonane, and decane. So these are our prefixes that will be pretty important moving forward, so keep those handy. All right, so look at each of these on your sheet. CH4 is methane. Your next one says C2H6. Well, it has 2 carbons, so what must it be called? Ethane. And then your next one says C3H8. 3 carbons, it must be propane. That propane you'd have in a gas stove or something. And here's what our structures look like. Notice they're all single bonds, and everybody's happy. If we figured out formal charges on all these, they would be 0. Okay, so what's an isomer? Well, when we've thought of something that has the prefix iso before, like isotope, what did it mean? The same. Okay, so it's something that's the same but has a small difference within it. So an isotope, remember, has the same number of protons, it's the same element, but it had a different number of neutrons. When we're thinking about structural isomers, we mean something that has the same formula but a different arrangement. So let's think about that butane. Here's my butane, 4 carbons in a row, and this is probably how you would draw it out if you saw this formula, but there's another option. And this one took 1 carbon and put him up top, but it's still the same number of hydrogens, the same number of carbons, so it's technically still butane. We call the first one N-butane, which stands for normal, And the second one's isobutane because it's an isomer of butane. Which one of these do you think would have the higher boiling point or the higher melting point? Well, we would really have to consider some intermolecular forces here and the bond angles, and it's going to be a little bit harder to get in here and break these guys up than it is to break these up. So isobutane has a higher boiling and melting point. Okay, so let's think about pentane. What does penta stand for again? 5. So if I have 5 carbons in a row, and this one looks a little different. Notice how they put the H's next to it? All they're saying is this one could have 3 H's, one up, one to the side, one down. This one could have 2 carbons, or I'm sorry, 2 hydrogens, one down and one up. Same with this guy. It's just a shorthand way of writing it out. So we still, though, have 1, 2, 3, 4, 5 carbons, which makes it pentane. Then we have this guy. How many carbons does he have? 1, 2, 3, 4, 5. Still pentane. How about this one? 1, 2, 3, 4, 5. Still pentane. What is different about these guys? Their shape and the arrangement of their hydrogens. But still, if we went through here and we counted up the hydrogens and we determined formal charge, they would all have the same exact number of hydrogens, and they would all have a formal charge of 0. But what do I name these guys? Well, one of them is going to be in butane. Normal is going to be the first one. Or sorry, pentane. I said butane. In pentane. This one's isopentane because he had a little deviation from the normal. And this one's neopentane. And the neo prefix just says that it's arranged in this tetrahedral fashion. Okay, but we have to be careful because don't all these guys look different? They do, but actually the only different thing is your angle, the way you're looking at it. This one just got flipped upside down to turn into this one, and he got flipped kind of a 180 to look like this guy. So if it's still coming off of the same carbon, there's still the total number of carbons, it's still isopentane. So don't be confused by that. Okay, when we consider making it a little more complex, we can talk about substituents. What is a substituent? Well, that essentially means something that's substituted for something else or something that's added in. And if we have these straight chain hydrocarbons and we add something to it, it becomes a branched hydrocarbon. Well, the way we named these is that we still use the longest chain and consider the parent name, and then we add this substituent name into it. Well, there are some really common substituents, and all we do when we see these is we take away the A and E on the end, and we add YL. So before, CH3 had that one carbon, and we were just going to call him methane because he would have been CH4. But now he's bonded to something, so that fourth hydrogen went away, and he's going to be bonded to anything else over here, and now he's CH3. So instead of methane, we call him methyl. Before, if we had 2 carbons, it would have been ethane. But it's bonded to something over here, so it lost a hydrogen. So now we call it ethyl. Same thing here. Used to be propane. Now he's propyl. And this one's just a differently shaped propane or propyl, so he's isopropyl. Notice the only difference here is how my hydrogens are distributed. So this one has 3, 4, 5, 6, 7. This one has 3, 4, 5, 6, 7. The way you're going to see the difference on these is with propyl, he's going to be bonded to the end and just be in a straight chain. With isopropyl, the bond is going to come here in the middle, and I think you'll see what I mean when I show you the next couple slides. So there's a table in your book, 22.2, that tells you a bunch of them, and here's a little snippet from that. The most important ones that you'll definitely have to know, at some point in your chemistry career are on this page. Okay, so let's practice naming a couple of these more complicated alkanes. What we do is we look at the parent chain and we determine what's coming off of it. and kind of name it based on that, and I'll show you what I mean. So here is an alkane. The parent chain is going to be the longest chain, so I have a couple options. I could go 1, I'm counting my carbons, 1, 2, 3, 4, and turn there and have 4 long. I could go 1, 2, 3, 4, 5, 6, or I could go 1, 2, 3, 4, 5. What's the longest? 6. So I'm going to use this long guy right here. And what's my prefix for 6? Hex. So hexane is pictured right here. And then I have to consider what's coming off of my hexane. Well, here's that CH3. Go back and look at your substituent list and find CH3. You're going to realize that that's methyl. I can't just call it methylhexane though, because that doesn't tell me where he's located, and if I was trying to draw this out, I would need to know where methyl was located. So what I'm going to do is go from the shortest end to get to that guy on my chain, and that's going to be this side, because there's 1, 2, 3 versus 4 this direction. So I'm going to put a 3 in front to show that he comes off the 3rd carbon, and call him 3-methylhexane. Makes sense once you practice it a few times. So 3-methyl, that's what he's called, and hexane's what my big guy is called. Eventually when you see this, you'll be able to draw them out. And keep in mind that if you see a structure like this that looks kind of crazy, all it's showing you is that you have a carbon at each junction here. And these carbons have the proper amount of hydrogens bonded to them to make them happy. It's just another way that we lazy chemists can draw these structures out. Okay, here's another. Find your longest chain, name it based on that, and then look at what's coming off of your chain, put a number in front, and name the guy. Try that, hit pause, and come back, and I'll have your answer. Okay, so what's my longest chain? 1, 2, 3, 4, 5, or 1, 2, 3, 4. Well, 5 is going to be my longest chain. What do I name something with a 5? Pentane. And then what do I have coming off of him? Well, there's another one that we were talking about, that methyl. And what number is he coming off of? He's coming off of 1, 2, 3. And even if I went from the other side, that would be number 3. So I'm going to call him 3-methylpentane. Pretty easy. Now, if there's more than one, we name them in alphabetical order, and we put di, tri, or tetra in there if we need it, but we don't use the di, tri, tetra when we're considering alphabetical order. So let's try this one. What's my longest parent chain? 1, 2, 3, 4. So I have 4 of them. Then what is my prefix going to be for number 4? Butane. And then what do I have coming off of butane? Will come from either end that you want. And you're going to end up at number 2, I have something coming off, and number 3, I have something coming off. So I'm going to call it 2, 3. What are these called? Methyl, and I have 2 of them. So I have to say dimethylbutane. So there they are, my methyls. They come off of number 2 and number 3. So I call it 2,3-dimethylbutane. As a scientist, when I see this, I know I need to draw it out with something coming off my 2 and my 3. What's coming off of them? Methyls. And how long's my parent chain? Butane, so 4. Try this one. Pretty complex, but you got it. Find your longest chain, name it, determine your substituents, and name those in alphabetical order, ignoring the di, tri, tetra. Come back in the next video, and I'll have your answer.